Hey, welcome back. In this video, we're going to tackle how to find the arc length of polar curves. To do this, what we're going to first use is this proven formula for finding the arc length of parametric curves. And if we're going to consider, we have a polar curve defined by RF theta so theta will go from alpha to beta, so we'll just write it like this. And then what we're going to do, we're going to use the fact that given this relationship right here, if we bring x and y into the game because they are up here, what we have is x equals r cosine of theta and y equals r sine of theta. So then, given a polar curve described as this, what we can do is just consider theta to be a parameter that are changing the value of r but specifically x and y. So what we can do then is instead of thinking of this t as a parameter, we just change these all to thetas. And now we think about alpha and beta not going for t from alpha to beta. We think about going from theta from alpha to beta. We have this setup. So what we would have in this case is we can just replace these statements with dx d theta and dy d theta. So then to find dx d theta and dy d theta with these equations right here, I first need to remember that r is also a function of theta. And so when I use differentiation here, because both of these will change, or these are expressions that are being multiplied together that change with respect to theta, I have to use the product rule. So in this case right here, if I differentiate both sides with respect to theta, well, I get, for this side, I get dx d theta. And then over here, I get dr d theta times the cosine of theta, then plus the derivative of the cosine, which is negative sine of theta, times r. Then, giving the same treatment to y here, if I differentiate both sides with respect to theta, I get dy d theta on the left-hand side, and I get dr d theta times the sine of theta, then the derivative of sine, which is cosine, times r. So then I now have expressions for both dx d theta and dy d theta, given this setup again, where we have this function r of theta, when theta varies from alpha to beta right here. But now to find that length, again, considering this theta in this case to be a parameter, because it is of x and y right here, plugging those in this case right here. So what I'm going to do is replace dx d theta with this beautiful statement right here, and then dy d theta I'll replace with this statement right here. Okay, so then what I've done is replace dx d theta and dy d theta in this expression right here with these representations given this scenario right here. And now I'm not going to do all of this work to FOIL these out and see all the terms, but I'll describe everything that happens here real fast. When you multiply this out, importantly, what you get here, this first term is dr squared d theta, or dr d theta squared times cosine squared of theta. Here, you're going to get the same thing with its dr d theta squared sine squared of theta. We're going to be putting those two together right there because they have these cosines and sine squared that will factor out the dr d theta squared. Then in the same way, we're going to get this r squared sine squared of theta, and this will give us out an r squared cosine squared of theta. So I just want to just wrap this up real quick. The other thing that happens is you get these terms that end up canceling out, two sets of this where it has actually all of these factors, the r, the dr, cosine, and sine, but they're going to cancel out in these cases given this setup right here. So what we have then, given that and given all this, is that our arc length described here, alpha to beta, is dr d theta squared. I'm going to add these together and factor that out. We know that becomes a 1 right there. And then in this case right here, do the same thing. Put those together. I'm going to get r squared times, factoring out from here, sine squared, cosine squared to get a 1. And still d theta. And there we pretty much have it. We now have the arc length, again, given this situation right here, from alpha to beta. I'll put this r squared, it's more classically, the r squared goes first, plus dr d theta squared, the square root of all of that jazz. All right, to wrap it up, if we have a polar function, r of theta, on the interval from alpha to beta, then we can calculate the arc length with this equation right here. where the length equals the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. A really important thing to add on here given this situation is that because we're integrating something that has the derivative of theta right here is that the function r has to have a continuous derivative. And again, to clarify, that's because we have to have continuous functions inside of our integral. All right, so let's do a couple examples. In this example here, we're going to find the exact length of r equals 5 cosine of theta on 0 to 3 pi over 4. We're going to use this. The only real work we need to do up front is to calculate this dr d theta, which just means we need to differentiate both sides of this equation with respect to theta. And we'll get, in this case, is negative 5 sine of theta. Then we just put them into the formula here. So in this case, the length is going to be from 0 to 3 pi over 4. The square root of these things squared, and I'm just going to square them when I plug them in here. So r squared is 25 cosine squared of theta, and then plus the derivative squared. This is also, that's 25, then sine of theta. Square root of all that, d theta. And then this is obviously going to get pretty straightforward here. What we're going to have now is I'm going to factor up 25 of that stuff on the inside and apply that square root. So let's write that out. It would be 25 times the cosine squared of theta plus sine squared of theta d theta, all with the square root. Applying the square root, well, we know that this right here is just 1. So really it becomes the square root of 25, which is 5. So all we're doing, applying the integral to, ends up being just a constant, which is pretty easy and rad. And that integral is awesomely easy. What I have then is 5 theta evaluated from 0 to 3 pi over 4. I can see the 0 is not going to do anything. Multiplying that, 3/4 pi times 5 is 15 pi over 4. All right, in this example, we're going to attack the length of the curve r equals e to the 1/10 theta on 0 to 6 pi. Before I even do the derivative part, which is always my first step, I want to look at an image of this polar curve, which, by the way, is pretty awesome. I really like these spirals, and this is a spiral that doesn't have this kind of consistent change in radius that r equals theta does, but then you can see that exponential kind of grow as this gets bigger. I always think spirals like this always look fairly hypnotic. I know, I love them. Okay, anyways, let's talk about the arc length. First thing we always do is to find the derivative of dr d theta. That won't be too difficult here. We have our friend, the exponential, which is very nice when it comes to differentiation. All I get is this chain rule of a 1/10 out of this, and everything else stays exactly the same. Then we just plug it into the machine here. So we've got the integral from 0 to 6 pi. First up, we have r squared. So if I square this, by the way, so if I raise this to the second power, since I have an exponent, an exponential expression, and an exponent, I'm just multiplying those together just to save myself a step here, right? So we'll just write it here. So if I have r squared, I get this, then I can multiply those together. So that becomes e to the 2/10, I'll write it as 2/10 theta. And then the same thing going here, I'm going to add squaring this, which just gives me 1/100th e to the 2/10 theta. Then these are like terms. These are both 1/5. I'll write that in here. So these are 1/5. And then I have one of them and I have 1/100th. So I can just combine like terms in this case. So 6 pi. So one of these would give me 101/100ths of e to the 1/5 theta. And we're still taking the square root, d theta. Last bit of algebra before I can integrate right here is to apply that square root to both of these expressions. So I can do that. Applying it to this would give me the square root of 101 over 10, because I can actually apply the square root nicely there. And then when I square root this, it's the same thing of raising it to the 1/2. And so this becomes e to the 1/10 again, d theta. So we're back to the e to the 1/10. And just to clarify real fast again, so when I'm applying it to this, just so y'all can see it, is that it's e to the 1/5 theta. And then what I'm doing is raising that to the 1/2 power. When I apply that square root, those add or multiply together to give me the 1/10 d theta. Then the integration is super easy because we just have this e function. We have this constant here. So I will just ignore the constant and let's just say let's pull it out. So square root of 101 divided by 10, the derivative or the integral of this, it always just copies itself. But in this case, since we're integrating, we have to divide out this factor of 1/10, right? Again, because if we took the derivative, we'd get a factor of 1/10 out. So to combat that, we need to divide by 1/10, which is the same thing as multiplying by 10. And then we're evaluating this from 0 to 6 pi. Then my 10s cancel obviously right there, so now I can evaluate by plugging this in. What I get in this first term is the square root of 101 e to the 6/10 pi. 6/10 ends up being 3/5, so we'll do 3 pi over 5. And then minus, we plug in a 0 to this, that goes to 0. This expression goes to 1, so we just get the square root of 101. And while it's beautiful to have these exact solutions, for some reason, looking at this beautiful spiral, I don't feel like that I have closure until I have a better idea of what that value is. And just so you know, this comes out to be just over 56 units.